Hello everyone, and welcome to today's presentation. I'm excited to guide you through the fundamentals of soil investigation, focusing on the bearing capacity test. On this first slide, we have the title, Soil Investigation, specifically the bearing capacity test. We'll look at the formula used to determine the net ultimate bearing capacity, which is QNet equals divided by Fs, minus the unit weight of the soil, gamma, times the depth, df. To make this clearer, let's consider an example. K is 450 kilonewtons per square meter, df is 1.5 meters, gamma is 18 kilonewtons per cubic meter, and the factor of safety is 3. Using these values, we calculate QNet as 450 divided by 3, minus 18 times 1.5, which results in 123 kilonewtons per square meter. If the QNet is less than 150 kilonewtons per square meter, that indicates weak soil, and in such cases, we need to choose a suitable foundation type like a raft or strip footing. On the visual side, we see a 3D soil model with a plate load test, which accounts for about 70% of the evaluation process. Additionally, there are 5 smaller reference images, including a borehole, SPT, plate test, soil profile, and bearing chart, to give you a comprehensive overview of soil investigation methods. That's a brief overview of what we'll cover today. Let's get started. Let's take a closer look at foundation selection and sizing. The general formula we use is A equals P divided by Q allow. Here, A is the area of the footing, P is the load from the column, and Q allow is the allowable soil bearing capacity. If the soil is strong, meaning it can handle more than 200 kilonewtons per square meter, we typically go for an isolated footing for each column. But if columns are quite close together, say less than 2 meters apart, we might opt for a combined or strip footing to distribute the load more efficiently. Now, if the soil is weak, less than 150 kilonewtons per square meter, we usually choose a raft foundation. This spreads the load over a larger area, reducing pressure on the weak soil. Let's look at an example. Suppose a column carries 800 kilonewtons, and the soil's Q allow is 200 kilonewtons per square meter. Using our formula, the required footing area would be 800 divided by 200, which is 4 square meters. That roughly translates to a 2 by 2 meter footing. On the visual side, we have a 3D comparison showing isolated, strip, and raft foundations, highlighting their differences. Additionally, there are some real-site images showing rebar placement, excavation work, formwork, pressure lines, and concrete pouring, giving you a practical sense of how these foundations come together in real construction. Let's take a closer look at isolated footing design. On this slide, we see some key formulas that help us determine the size and strength of the footing. First, the area A is calculated by dividing the load P by the allowable bearing capacity Q allow. This tells us how large the footing needs to be to safely support the load. Next, the moment M is calculated using the formula Q times B squared divided by 8. This helps us understand the bending moment that the footing must resist. Similarly, the shear V is found by multiplying Q by B and then dividing by 2. This gives us the shear force the footing must withstand. To make it clearer, let's look at the example provided. If P is 800 kilonewtons and Q is 200 kilonewtons per square meter, then the area A calculates to 4 square meters, and the moment M comes out to 100 kilonewton meters. The visual on this slide shows a 3D view of a footing under a column, with arrows indicating the moment and shear forces. These help us understand how loads transfer through the footing. There are also close-ups of key details like the steel cage, anchors, soil bearing capacity, plan layout, and reinforcement bars, which are all crucial for ensuring the footing is both safe and effective. Remember, these formulas and visuals are fundamental in designing a reliable, isolated footing that can safely support the structure above. Let's talk about strip footing design. On this slide, you'll see some key formulas that help us determine the dimensions of a strip footing. The first formula, Q equals W divided by L times B, is used to find the actual pressure exerted by the load on the footing. W is the wall load, L is the length of the footing, and B is the width. The second formula rearranges that to find B, the width of the footing, which is W divided by L times the allowable pressure, Q allow. This way, we can ensure the footing is adequately sized to support the load without exceeding the soil's capacity. For example, if we have a wall load of 200 kN per meter and an allowable pressure of 150 kPa, we can calculate the required footing width as about 1.33 meters. This helps us design a safe and efficient foundation. Now, visually, you'll see a 3D illustration of a long, continuous footing under a wall, which accounts for about 70% of our focus here. The other 5 images show important construction details: the trench preparation, placement of reinforcement mesh, continuity reinforcement for structural integrity, wall starter bars, and proper compaction techniques. These visuals highlight the key steps in constructing a strip footing, emphasizing how each component contributes to a durable and stable foundation. Understanding these concepts is essential as we move forward in designing and building safe, reliable structures. Let's take a closer look at the raft foundation, also known as the mat footing. First, I'll walk you through some key formulas we use to analyze it. The first is Q equals the sum of all loads, or sigma, divided by the area of the raft, A raft. This gives us the pressure distribution across the foundation. The second formula is for the moment, M, which is calculated as the weight, W, times the length squared, L2, divided by 8. This helps us understand the bending, stresses the raft might experience. Now, to make this concrete, let's look at an example. Suppose the total load on the foundation is 18 mN, and the raft measures 9 by 9 meters. Using our formula, Q equals 18 mN divided by 81 square meters, which results in approximately 222 kilonewtons per square meter. This pressure value is crucial for designing the foundation to safely handle the loads. On the visual side, we have a 3D color-mapped representation of the raft, showing how the pressure distributes across its surface. You can see areas of higher and lower pressure, which helps us identify potential stress points. Additionally, there are 5 reference photos that provide practical insights. The mesh layers used for reinforcement, waterproofing details, the concrete pouring process, the joint details, and drop panels. These visuals connect the theoretical calculations to real-world construction practices, emphasizing how each aspect contributes to a solid and durable foundation. Understanding these concepts is vital as they tie into the overall foundation design, ensuring safety and stability for the entire structure. Now, let's look at the column design. The key formula here is PU equals 0.4 times FCK times AC, plus 0.67 times phi times AS. This helps us determine the axial load capacity of the column. For example, if we consider a 300 by 400 millimeter column with 4 20 millimeter diameter bars, and assuming a concrete strength FCK of 25 MPa and steel yield strength phi of 420 MPa, we get an approximate axial load capacity of about 1.9 meganewtons. It's important to differentiate between short and slender columns. If the effective length divided by the radius of gyration, LF over R, is less than 12, we're dealing with a short column. For these, the formula we just discussed applies directly. However, if the column is slender, we need to check for buckling. The critical buckling load, PCR, can be calculated using the formula pi squared times E times I divided by LF squared. This helps us assess the stability under axial loads. On the visual side, you'll see a 3D reinforced concrete column with load arrows indicating about 70% of the capacity. Additionally, there are supporting photos showing key construction details like tie spacing, cage installation, cover blocks, plumb checks, and shuttering. All of these elements come together to ensure the column is designed and constructed properly for safety and durability within the overall structure. Now, let's take a closer look at the pedestal, or neck, connection. The key formula here is as equals PU minus 0.45 times FCK times AC, all divided by 0.87 times phi. Essentially, this helps us determine the amount of reinforcement needed to transfer the load from the column to the footing properly. It also ensures that the reinforcement remains continuous, which is crucial for structural integrity. In the visual, you'll see a 3D model highlighting the column-to-pedestal joint, which accounts for about 70% of the connection detail. We've also included 5 close-up images showing critical details: starter bars, column dowels, top ties, anchor bolts, and the epoxy interface. These elements all work together to ensure a strong, reliable connection that transfers loads effectively and maintains alignment throughout the structure. Remember, paying attention to these details is vital for the overall safety and durability of the building. Let's take a look at the beam design, focusing on flexure and shear. The key formulas here help us determine the required reinforcement and shear capacity. First, for bending moment, we use mu equals W times L squared divided by 8. This gives us the maximum moment for a uniformly distributed load. Next, to find the required steel area, we divide mu by the product of 0.87 times phi, and the lever arm Z. This tells us how much reinforcement steel we need to resist bending. For shear Vu, we multiply 0.5 times the width of the beam, B, times the effective depth, D, and the concrete's shear stress, Tauk. This helps us check whether shear reinforcement is necessary. Let's look at an example. Suppose the span L is 4 meters, and the load W is 6 kilonewtons per square meter. Plugging into the formulas, we get a maximum moment of 12 kNm per meter, and the steel area as needed is approximately 380 square millimeters per meter. Now visually, we see a 3D model of a reinforced concrete beam with the bending moment diagram, which accounts for about 70% of the slide. Surrounding that, there are 5 smaller photos showing the stirrup layout, bar bending, concrete pouring, form removal, and crack control. These images illustrate the practical steps in the beam's construction process. Overall, these formulas and visuals help us understand how to design beams that are both safe and efficient, ensuring they can handle the anticipated loads effectively.